All right, guys. So I just wanted to finish up these notes that we didn't quite finish up in class today. And we were starting with the third factor related to dictating stroke volume. Right? So we had preload. We talked about that. Afterload, we talked about that. And now we're on contractility. So the question of what is contractility? And as we've mentioned before, this is really just how hard the heart is beating, the force of contraction. And really what determines this in the body is how much sympathetic nervous system activity we have. The more sympathetic nervous system activity we have, the stronger of a beat we get. And so we'll look at that in a sec as to why, what physiologically causes that stronger beat. But before we get to that, what we use to measure contractility, and we've already mentioned this before, I've already mentioned this before, is ejection fraction. So again, remember ejection fraction was the percentage of blood that comes out of the heart. So we calculate that by ejection fraction equals stroke volume divided by EdV, and then we times that by 100 to turn this into a percentage. So normal stroke volumes are normal ejection fractions are around 60% at rest, and these can go up as we move into exercise. And all right, so that's kind of the basics of contractility. Now let's take a look at what this means. So what this means really is if this curve here is kind of our normal Frank-Starling curve we just talked about, where we have preload on the x-axis, stroke volume on the y-axis. If contractility goes up, then for the exact same preload, which would be on this dotted line here, right, we get more stroke volume. Okay, so going from here up to here, all because of more contractility, right? So the same amount of blood started in the heart as we did, so the same end-diastolic volume, but we get more of that blood out. So really what that means is if we have the same EdV, so EdV equals no change, right? But stroke volume equals up. And remember, stroke volume equals EdV minus ESV. So then in order to get stroke volume up, if we know EdV didn't change, then we have to make ESV smaller, right? So ESV must have gone down in this situation here to go from this stroke volume with the same end-diastolic volume but a higher stroke volume. So that if we know end-diastolic volume didn't change, we know ESV did, and it went down. So that's really what happens. With more contractility, we get more of that blood out of the heart. And that makes sense how that would increase the ejection fraction, right? So we went from starting with the same amount of blood, and then let's go back to the previous slide. So if we started with the same amount of blood, so EdV did not change, right? But stroke volume went up because of that lower ESV. Then stroke volume goes up, EdV stays the same, so the numerator goes up, denominator stays the same. That's going to increase our ejection fraction. So that's what that does. And the mechanism here is really interesting. And so what we see here again is sympathetic stimulation is going to increase, and this graph is a little bit different. This graph's a little bit different. This one is cardiac output on the y-axis, and really preload on the x-axis. And we see for the same preload here, if we have sympathetic stimulation, we're going to get higher cardiac output. Okay, and that's going to be related to both an increased heart rate and an increased stroke volume. Okay, but then for that same preload, if we have parasympathetic stimulation, we're going to have a lower heart rate. Okay, so that's part of why cardiac output is lower, but then we're also going to have lower contractility because contractility decreases with parasympathetic control. So what's the mechanism here? The mechanism is as we increase sympathetic tone, that sympathetic activity, just like when we do this with increase in heart rate. So we have that SNS activity leads to increased norepinephrine release by the cardiac accelerator nerve, right? Cardiac accelerator nerve releases norepinephrine. The effect of norepinephrine on the heart is depolarization, right? So norepi, as well as epinephrine in the blood, causes depolarization. Okay, and we talked about how that is partially from the sodium, but it's also partially because we have an increase in calcium influx. Right, so calcium goes in. So what else does that calcium do besides depolarize the membrane? It also goes in and binds to troponin. And if it binds to troponin, then we know that that is going to lead to increased actin myosin binding. And if we got more actin myosin binding, we're going to get more force, a more forceful contraction. So that is pretty much the mechanism that sympathetic nervous system activity uses to increase contractility. Okay, so one more question like this. We'll deal with this a lot more in the TBL days, but which of the following has the greatest ability to increase during exercise? We already looked at this, going from about 0.5 to about 3.5 liters, right? So that's a 7-fold increase. We talked about this going from about 50 or 60 up to about 100 to 120. So that's a 2-fold, okay, increase. Heart rate, we know, can go from about 60 beats per minute to probably about 200. So that's about a little over a 3-fold, maybe a 3.2-fold here, okay. And then we know cardiac output. We haven't really talked about it too much yet, but probably somewhere around 6 liters per minute at rest, up to maybe about 20 liters per minute or 25 liters per minute. So that would be about a 4-fold, 3.5-fold increase. Let's see if I remembered my slides well and see how close that was. Oops. There we go. Yeah, so about a 2-fold increase for stroke volume, 7-fold increase there. From about 5 to 25, about a 5-fold increase. So I was a little bit off on my cardiac output one. Sorry about that. I was testing myself, seeing how much I remembered. And then heart rate about 6 to 200. That's about a 3-fold increase. So of these, still our inspiratory capacity is by far the greatest. All right, guys. Well, that's it. Have a great weekend, and we will see you next week.